Okay, let's keep that in mind. All right. So we are going to start with the data iteration, and first thing we are going to talk about is data-centric AI development. Okay, so there are two views that we have in basically AI development or ML development: model-centric view and data-centric view. Okay, so in model-centric view, which is the concept of what happens in academy, it's you have whatever data you can collect, and basically you start building more models, better models every time. The whole idea is that I have a fixed amount of data and I just basically build better models every time. Okay, so that becomes model-centric view. Again, all the data fixed, iteratively improve the code. Now, on the other end, data-centric view, which is what happens in the industry, is that where you're constantly getting new data. You're just having this data pipeline that the new data keeps coming, And when you have a scenario like that, when you keep getting new data, your focus is more on the data and data processing and data pipeline, because if I can improve my data quality, I know downstream model also will be better, So instead of constantly trying to have a better model, you actually keep the model fixed and you just improve your data quality. So that becomes model-centric view, it becomes data-centric view. And again, in industry, we do data-centric view, and in academy, we do model-centric. Okay, so that's the main difference here. Now, let's, first thing we're going to now go over is just becomes a part of our data iteration. We're going to discuss about the data augmentation, and I know you all have done some sort of augmentation, probably in some projects, in some sense. But let's say we are doing some speech recognition, and you have different types of data, input data. So you have data with the background of car noise. That is, it is the speech recognition. Some people are talking, but you have a background of car noise. You have plane noise, train noise, machine noise, cafe noise, library noise, and food court noise. Okay, so it's all like different types of noise that you have in your data. Now, by default, if you're looking at these types of noise, you can see that the first four is kind of like similar. They're kind of like a machinery noise. And the last three are basically cafe, library, and food court. They're like a noise of backgrounds, like where other humans are speaking, right? So that's kind of like the scenario here. Now, you are doing a speech recognition example, and we know speech recognition is kind of like a unsupervised task. So we know human level performance is a really good, basically baseline that if you want to compare to. So you do a test using human level performance for all basically data types that you have, and you find out, the green line is the performance that human level basically give you. And then you develop a model. Your model is the line on the bottom. That's your model. And you notice that, you have different basically performances depending on where is the, what type of data basically you have. And you basically, what you notice here is that the first four types, which is the machinery background, machinery noise, you actually have a pretty close basically performance in compared to human level performance. And however, for the other three, library noise, cafe noise, and food court noise, you see the performance is much lower, right? So now the idea here is that I wish that we have another model. We could improve our model maybe to reach here. Maybe we could have similar gap between these three types and same as this four, and the human level performance. That's the ideal scenario maybe for you. Now, one of the scenarios that you could improve a data or like a model like that is that to focus on data augmentation, and data augmentation means that I have three types of data that I'm doing bad on those, Maybe I could augment those three types, and like basically by augmentation, means that you're making some sort of like adding some specific sort of perturbation to the actual data. And you need to ensure that that perturbation does not basically ruin the nature of the data. That means if someone in the audio says hello and you add some perturbation to it, you still should hear a hello, right? If you hear all of a sudden another word, then that means you just change the data. You can't do that. So data augmentation become basically a steps that we're going to introduce here. And it's really important to remember the goal of data augmentation is that to create realistic data over the data points that your model does poorly on this, but you need to ensure that, that data is basically should be realistic. If you change the data again, change the nature of the data, it's not used. Because if you, as a human, as an unsupervised task, you cannot understand or read or look at an image that you perturbed to classify it, for example, then we shouldn't expect that the machine also to do that. It becomes really challenging. So one analogy here is it's actually called like a rubber sheet analogy. The idea here is that if we look at the example that we have, these three, they are where we want to add improvement, right? Now the question here is that which one of these three should I focus on? Which one of these three should I augment? Should I augment all three at the same time, or should I augment one of those? This rubber sheet analogy basically says that if you look at these three, the caffeine noise is lower than all three, right? It's possible if you augment caffeine noise, it's kind of like, imagine you put a rubber sheet around this and you pull the caffeine noise up, it automatically will pull up the adjacent, basically data types. So instead of trying to add for all three, figure out which one of them will benefit the most, from the augmentation, and apply the augmentation to that one, and see what will be the impact of that on the other ones, the adjacent ones. Because when you look at this example, we know that these three types of data, you have similarities, right? So if your model learns to improve, basically be able to improve a classification on this one, it has learned something about that type of noise in the background. And that might automatically improve the other ones. So when you talk about data augmentation also, it's really important to understand that how much to augment, like which one to augment, right? If you just augment all the data, you actually might not see the benefit at once. Just maybe it's better to do iterative basic augmentation. Add to one of those categories, see the impact, and maybe add to the other one, see the impact, and so on. Okay, so now this is an example of, again, an image basically augmentation, and you have this data that there's a scratch here. I know it's normally really hard to see on this screens, but so imagine there's a scratch here, and you augment the data. So this one is, you flip the screen, we still see the augmented, like the scratch. So this one basically we add more brightness, you still see the scratch. But this one you added more darkness, now you don't see the scratch. So this is an example of a bad augmentation because you cannot see it, and then we shouldn't expect that the machine also to see that. So overall, basically, if you have some scratch here which is not that visible, your goal might be that hey, what if I basically, as part of augmentation, maybe I put some circle around it, that shows that hey, this is where the area or where the scratch exists. Overall, as everything in ML, data iteration is also a loop, right? So you need to basically add some amount of data, do a training, do some error analysis, and then add another amount of data, and so on. Always, also, it's kind of like a rule of thumb: don't add more than 10% of the 10% to your data at once, because you don't. It's kind of harder to understand what basically caused the model improvement. If you add all of a sudden lots of data, you actually don't know what caused that improvement. So try to basically add a small amount of time at a time. Now, the question here is that, will adding the more data hurt, or can it actually hurt the model performance, right? So this is like a kind of like an observation overall, But it's basically is that when you deal with unstructured tasks, unstructured data, if it depends on what types of model you have technically. If you have a model that's larger model tends to have low bias. They have basically high variance, but they tend to basically have a lower bias. That means they do a great job on basically the task, the larger the model gets, right? So if you're having a large model and the data, the types of augmentation or data that you're adding is kind of clear mapping between X to Y, then adding more data actually doesn't hurt. Okay? This is a scenario, like if you have a larger model and you have a data that has a clear mapping. But if you basically have smaller types of model, that adding new data can easily, add noise to the model. And we're going to talk about it. Now let's look at this example. This is an example of, I think it's a company that they were using Google Street View to read like a house numbers, basically, And what they found is that there are certain states in US that house numbers could also have letters in it, alphabet, right? Mainly, for example, here is all digits, but there are certain places that you can have basically alphabet characters. And what they found was that wherever there is an I in the house number, basically they're doing a really bad job. Like the model is not capable of basically reading that I. It always reads it at 1. Okay, so the idea here was that let's do augmentation. Let's add lots of images basically with I. Different types of I basically in the image. One of those I's was something like this, for example. All right, and you can imagine what happened. The model ended up overfitting to I and start doing really bad on 1. Why? Because despite the fact, yes, we add some augmentation, but this also could look like a 1, right? So it basically, it adds, basically makes it more challenging for your model to detect if this is an I or this is an 1, right? So it did hurt the performance of the model. It's a scenario of that when your augmentation is not good. Okay. Now, when it comes to structured types of data, like we deal with the structured data, adding more data is not that straightforward because having labels is not that easy for structured data. But let's look at this example of a restaurant recommendation. So you have basically this app that basically recommends restaurants. But what happened here is that every time someone is vegetarian, for example, or vegan, they go to your basically app and they don't get a proper recommendation. Okay, that's because your app is always just offered them a restaurant that maybe always sells meat, right? And the idea here is that how could we improve that? How could we help that model to learn something like that? In structured scenario, you add more features instead of adding more data, right? So what you could do is that possibly add some features. For example, if you know the person is vegetarian or vegan based on the performance, based on the history, they never ordered, for example, anything that's contains meat, then you maybe could create a column that says vegetarian or not, for example, right? And then you can also parse out the restaurant's menu and see that if this restaurant offers vegetarian or vegan food, right? So that's how you could basically improve your model by adding more features. In compared to in unstructured, you add more data because it's easier to acquire more data. Okay. Now, there's actually one interesting that I personally you have definitely seen it. If you go on, for example, Grubhub or any of these apps that you want to order food, right? And select healthy, all right? Put a filter and select healthy, right? And you'll see the healthy options that you get. It's like a Taco Balls, McDonald's, they all come up as healthy, right? So now the idea here is that, okay, well, I know that's not healthy, but why those are coming up as healthy, right? So from the app perspective, they need to add a feature that says that, okay, if someone says healthy, this doesn't consider healthy. But also that could introduce bias toward other companies. Why? Because if I tell to my app, like my app says that your food is not healthy, how do I know? Right? Who am I to say, right? So how did they know that if this food is healthy or not? Probably when the company creates an account and basically introduce the meal, they introduce the meal as healthy. They check that, like you have this option, select what you are selling, they select this is healthy. So when you promote it as healthy, right? And test it out. You definitely see that. The first row comes Taco Bell, McDonald's, and stuff like that. So now, maybe they could just add a feature that, potentially, not that they call it is not healthy, but maybe have different types of information, contextual information that healthy, but consider the calorie amount, some additional information. Now, let's do another example. Let's say you basically do a food delivery, it's a similar thing. So, and you only basically have tea, coffee, or pizza, and you want to basically say that using these signals, and how could you recommend? Like, what should we recommend to a user? What do they want, right? And there are different ways that we can decide to do recommendation system. And the simplest one is collaborative filtering, which the idea behind collaborative filtering is that you look at a user and you find similar users and see what similar users they do. Sorry, that. What similar users do order, and then based on that you basically offer them something else. The problem with collaborative filtering is that if someone is basically called the user zero, that is someone that comes to your system for the first time, how could you offer them something? You don't know anything about them, right? On the other hand, you have context-based filtering. And context-based filtering is that, for example, you create some contextual, basically, representation of users, restaurants, and their foods, right? So in that scenario, if basically something new comes to your server, even a restaurant, a new restaurant comes to your basically app, you haven't seen that before, but you already know the food menu. From the food menu, you can find some sort of like a similarity with other restaurants, and you do recommendation, even if that restaurant never had any rating on your system, right? So we are basically doing a shift from collaborative filtering to context-based filtering because it's kind of like a really black and white. If you look like this user, you probably like food, their food, what they basically like, right? However, in reality, that's not the case. So context-based filtering is more better because you find a representation like an embedding for the user, embedding for restaurants, embedding for their food. And based on that, you could have some contextual basically representation or basically recommendation. Now, same scenario here is that in structured data also it's iterative loop. However, there are a little challenges here because the error analysis in the structured data, it's more challenging because you don't have human level performance to compare to. Right, so the error analysis could be a bit more challenging. And what you also need to keep in mind is that you need to have some sort of like a user feedback when it comes to structured. That's the best way of labeling data. If you collected user feedback, if they give you the feedback, thumbs up, thumbs down or something, that's great. But you also need to basically somehow maybe compare to competitors in the market to see that, hey, okay, if we are doing good or bad. In unstructured, we didn't have this problem because you can just figure out, do some labeling by human levels and or experts, and then compare your result with those. But in the structured data, that's a bit more challenging. Now, the next thing as part of data iteration, we're going to talk about is called experiment tracking, which today we also have a lab on MLflow for experiment tracking. The question here is that, what is experiment tracking? Anyone here can tell us? What do you think is experiment tracking?
When we run multiple models, we have to store all the hyperparameters of the model, like which model gives the best result, we have to use those.
That's
to
good.
see the performance of all the models and select a model, we store all those in a place that is.
All right, that is good. That's correct. What else? Anyone else? Yes.
You can take observations during the entire experiment for analysis after the experiment.
All right, that's good. So think about this experiment tracking is that you have probably worked on other projects before and you have all these Jupyter files that you basically you run a model, you save the model, give it a really long name and put it maybe in a folder, and you run another model and just piles up, right? And at some point, it kind of becomes difficult to figure out what you were doing, which one was better, which one should I use, what did I use as part of the training this version versus the other version, right? So those are the challenges that we have. Now, the idea of experiment tracking is that could we basically have a framework, that when we want to do an experiment, like from the start, could we start keeping track of the hyperparameters that we use, keeping track of the data that we use, the model that we ran, the result of the model. Could we have a dashboard for visualizing it, for doing a comparison and stuff like that, right? But the question will be that what to track for, right? Okay, it's like, okay, let's say we want to do that experiment tracking, but what should we actually track for? And things that you could basically track for could be your code versioning, which, we do that with GitHub, basically. Data set that you used, we basically, the idea here is also is that to keep track of the data versions that you have as the data comes. You can do that with some tools like a data version control, like DVC. It's really similar to concept GitHub. We will have a lab on those later. It could be your hyperparameters. It could be your results of that your model has. And then what are the tracking tools that you could basically use? Before this experimental basically experimental frameworks become popular, it was either a text file a spreadsheet that you keep track of your models and your experiments. But now you can have this experimental tracking system that makes it much more desirable. Now, also, the desirable features that basically you need to collect is that what data do I need to be able to replicate some specific result? You need to have some analysis over the result. Probably you need to monitor for your resource, like how much CPU, memory, GPU, like all those utilization. Maybe you could also monitor all of those, right? And maybe at first you don't need to write anything basically in-house, and you could basically outsource all of these tools, which just makes it much easier. Now, the next thing we're going to just go over is going to be, again, this is all part of the data iteration, from big data to good data. And one thing that's important here is that to remember that having lots of data, it's not the key, okay? And again, this was, if you go like 5 years back and search like this we were in era of big data. Everyone was talking about era of big data, like all the companies, right? But now if you go, most of the companies, they invest a lot on the data engineers, right? Why? Because I care, like as a company, I care more to have a proper pipelines, proper basically processes in place that I can get any data and clean it in a proper format. So my other teams could work with that clean data. Instead of just saying that, oh, I have lots of data and it's good. No, having lots of data, that doesn't mean you can use it actually. Okay, so the era has changed, it's just be sure we are focusing more on good data instead of big data. Now, so we're going to go over the next thing, collecting and labeling data. Yes?
Is Zoom recording it? Like, I'm not sure.
It does record. So it's recording from the screen here, right? So, all right. Now let's take a moment and read these two. So these are two code by one of these from the Uber, the other one is from Gojek. Basically says data is the hardest part of the ML and the most important piece to get right. Broken data is the most common cause of problem in production ML system. And from Gojek basically says that no other activity in machine learning lifecycle has the higher return of investment than improving the data that model has access to. As a reality of it, most of the larger companies, they basically spend more time on this. And if you also look at the job market, you find more job for data engineers than other data science or maybe ML engineers. Because if you have data, you want to be sure that data is clean and accessible. Now, so I think we do need this, so just go here. Traditional ML pipeline so far has been that you do something like that. You have a data, training, evaluation, and that will basically gives you a model. And this is basically what you have. That was the traditional ML architect. And we have talked about this, that now in reality in ML production, that piece is going to be only this part, a small piece or part of the project. And as you can see, configuration, data, feature, data verification, those are all becomes a major part of this production that you have. Now, let's do again comparison between academic and industry. So when it comes to data, industry basically is dynamic shifting data, academic is static data. priority in design, in academic, highest overall accuracy, and industry is fast inference and good interpretability, right? So it's kind of important to remember in industry, we still want a good accuracy, but you'd rather to have maybe a small amount, like a higher error for a certain amount, not too much, but you get a faster one, right? Because it's just from the cost perspective, it's much better to have a model that has fast inference. Also, your model has good interpretability because now you have customers, so you want to be sure that you can answer why was the reason of certain decision. When it comes to model training in academy, you focus on optimal tuning and training. In industry, you focus on continuously assess and training. Fairness in academy is really important. It wasn't important probably before, and recently it's getting more important. And industry is crucial. It's so easily you can basically lose a business if you haven't accounted for the fairness. The challenges that industry has, academy has, is high accuracy algorithm. In industry is entire system. So you can basically balance, to compare these two and to figure out, how more challenging or how much more challenging is it if you shift from here a carrier to basically here, right? It's kind of like it's not that easy to be able to have all of that at one go, basically set up. And that's why lots of, I think it's like about actually 80% of the data science projects, they never basically become a product because, it's actually got lots of challenge in the industry. So when we talk about production machine learning, you need to basically look at it as machine learning development plus modern software development. That's basically what it means, production machine learning. You need to have a really good, basically, ML development, but also you need to, by nature, to be a good software developer. Okay, so that's the reality of that. Now, right. Now, when it comes to the life cycle of the data, you need to basically think about the full life cycle. It starts from labeling, which, the task of having labeled for your data. Then it comes to feature space coverage. And anyone can tell us what's feature space coverage? What do you think is the meaning?
It mean like how many features, I did cover all the features necessary for it, or?
No, so it's not talking about that. The feature is space, not the number of features.
I think if you have different features and there are different variations of those features, you want your data to cover every single combination, or at least like touch different samples, cover the entire combination space of the individual feature.
Which you're on a great track, but which space? Like what's the space that we're talking about?
Let's say if one label is small, medium, large, then you would like some samples to cover small, some samples to cover medium, and some large. Obviously, for numerical values, it might be different distribution.
Great answer, but there's something missing. Let's see if someone else picking up that.
I mean, not to build on his answer, but just thinking about decision trees, when the way the algorithm works out is it partitions data based on the difference in values, right? So if your features are able to cover all the range of those values and your entirety of your data can be partitioned with help of those features.
That's correct, but something is missing. Where is the feature? Where is the space coming from?
Does it refer to the scope of the project? Like, if you're kind of dealing with a certain industry, does it have to involve data from everyone who's related to that industry, or just that particular?
So that's smart. So all of this, as you say, is correct, but the part here is missing is that when you say feature space coverage, it's not about your data. It's about anyone else that they want to use your product. Did you cover their feature? Feature space means that you don't cover only feature space of your sample data. Your feature space should be large enough that if someone that's not part of your training data, they still could use that product. Like, let's say example is that for example, you're covering for a certain demographic, like for a certain product, and you have, I don't know, like age, let's say age you have. And in your data, age starts from, I don't know, like 24 to 60. From your data perspective, that's the feature space, from min to max, right? But your customer starts from 60. So your feature space is not covering the potential customers that you're going to have. So feature space coverage is that you ensure that the data that you have can cover the entire population that you're targeting. Right? That becomes the feature space coverage. Then minimal dimensional, again, is always we rather to have a less dimension because it makes it also cheaper or maybe also but easier to train models. Maximum predictive data. Now, what do you think of that one? Yes.
Data you train it on, the more precise it might be. So it's like when you can maximize the input to output data which you have before you start training, it gives a better.
I mean, more data doesn't mean more like a maximizing the predictive signal, or predictive data.
Is it related to higher confidence in data?
No, so it comes around the ensuring that when you do feature engineering or you do feature selection, what do? You look at all your features and you try to see what features should I create to improve the basically detection rate, right? What should I add improve my model accuracy? Which features should I get rid of because they add noise to my model, right? So that becomes something like a maximum predictive data. Then fairness, and who can say that one? What do you think is fairness when it comes to data?
You have equal amount of classes of data. Like if you have two classes, you have equal amount of data. Yeah, for
Okay,
the
equal
both,
amount of data. What else?
for the classes.
That's correct, but it has more definitions. Fairness. What else?
It's capable of identifying both classes, but also having a measure to see if it can balance between precision and speed.
Okay. So these are correct. Yes.
Accounting for rare scenarios.
Yeah. So all of these are correct. Fairness is actually a really like a wide definition. Like it could cover so many things. But overall, around data and fairness, fairness basically means that to ensure that your data basically can. Let me see. Someone is. Ensure that your data can cover basically every groups that you're targeting. Ensure that your data basically like you have same ratio for everybody. If you're, for example, if you're looking at maybe the labels that you have, is there any basically bias in that data? That means, let's say you're doing a classification and you have same ratio for two classes. But when you're looking at the labels that you have, one class gets 90% class, like a label that's one, the other class got, I don't know, like 10% class, right? So that basically means that there's some for that population. So fairness is also becomes really important and crucial that you need to keep in mind. All right. And then rare condition, again, as your friend also here, so that you need to be sure that you have accounted for, the rare conditions, rare scenarios that could happen. And you remember we talked about that large data, especially you have the problem with the long tail, that actually something that you need to basically take into account. Yeah, so that was around the data. Now you need to basically think about also from the software perspective, what should I account for? You need to account for a scalability. Scalability means that if whatever software I'm building is able to scale based on the traffic that I have, scale up or scale down, for example. Extensibility, that means that build your product somehow, your pipeline somehow that you can add something to it as you go without a need to breaking the pipeline, right? So you can basically add something to it. Configuration, does it have a proper configuration? Does it have all the necessary details that I need? Consistency and reproducibility is okay. Is this consistent? Can I reproduce a result? Safety and security, which is pretty also important, is the model that you have safe? Is it secure? Can someone basically break into it? Can someone extract data out of it? Modularity, the code that I have, is it modular? You know, the modular code means that, you know, instead of writing maybe large codes, maybe write a smaller code that they do a smaller task, you know, so rather than having your codes to be large. Testability, can I test my code and basically my pipeline end to end, you know? Monitoring, you know, do you have a proper monitoring from data perspective, from your model perspective, input, output, you know, do you have those monitoring? And overall, does it follow, you know, common, you know, like a software, basically best practices? So you need to think about like this when you, whatever you are building from the data perspective, there are a series of questions we talked about, but from software perspective also, you need to think about this type of things that, you know, it's kind of maybe create a checkbook for yourself, you know, can you basically check this out? Hey, yes, I have all of this. Now, here's so we can complete this. So overall, basically, what we basically have here is that we start with the scoping, you define a project, okay? And then we basically add, yeah, this becomes the, after the scoping comes the data. After the data basically comes to modeling, okay? And then you have this deployment and monitoring. Okay, so this is basically 4 steps. So these are all connecting, but as you go to basically do deployment, now there are a couple of scenarios. That's why we're saying that these are all kind of like a loop. You could go back. You could be in modeling, and you figure out something doesn't work, and you go back on your data. Right? It's kind of like a loop. And when you develop a model, you're like, oh, you know, this model doesn't land. Maybe I need to improve my data. You go back and maybe you fix your data. You could be on deployment and you figure out there is something is wrong with your model and go back, fix your model. You could be on your deployment and figure out there's something is wrong with your, like something you need to change about your data and just basically go back here. And you could be here and go all the way back to scoping because you're like, whatever we built doesn't work. We need to change the scope. You know, we need to basically have a different view, basically. Right? So when you look at this ML lifecycle, you need to look at it as a loop because it's a loop. You know, as you go through, you need to basically be able to go back to different stages and basically iterate. Is that clear? So now, when it comes to challenges, basically in production grade ML, the challenge is basically building the entire system, building an integrated ML system. That's the main challenge. And you need to also be able to continuously operate on it. You need to be able to continuously monitor for data that comes here. Like is there any change in the data that you have? Also, you need to be sure that whatever you build is optimized, you know, from the resource and cost perspective. Okay, because you know the last thing you want is that you have a good model, but then it's just pretty expensive. You won't be able to use it. Now, we're going to do basically a channel to this called like a pipeline. Now we're going to start talking about pipelines. The first thing we're going to talk about is going to be ML pipelines. Okay. Now, so we're going to go over the definition of ML pipeline, and we're going to start with the basically DAGs and then like pipeline orchestrations. And then we're going to start basically work with TensorFlow extended or TFX, you know. So let's just start with ML pipeline. So what's an ML pipeline? ML pipeline is an infrastructure for automating monitoring and maintaining model training and deployment. So that becomes the definition of ML pipeline. Infrastructure for automating monitoring, maintaining of your model training and deployment. Now, this is a interesting, like a really nice chart by CD Foundation of just like an organization. What you see here is that it's just a view of that CD Foundation has on the ML pipeline. Every other papers, every other companies, they have something similar. Different website, you will see a different image. But one thing you will see that they all have common steps. Comes from data, model development, deployment, monitoring. But maybe the breakdown is different, you know, but the whole basically idea is the same. Now, the CD Foundation basically starts something like this, that you start with data, meaning ingestion, analysis, validation, feature engineering, you do some splitting, Then you go basically to model building, you build the model, you do some optimization, you validate your model, you train it basically at the scale that, you know, okay, this is a good model, let's build it at scale. Now you have a model, right? So then you deploy your model, depending on where you're deploying it, is either cloud-based or edge-based, like an IoT core. Then you serve that model, new data comes, you basically serve that model, you monitor the model and log, and you check for explainability of your results that you have. You decide on fine-tuning and improvement, and this could go all the way back to here, build the model. So that's the ML basically pipeline definition by CD Foundation. Okay, and again, different companies, they have different view, but they all have common basically steps. So now, directed acyclic graph, okay, or DAG basically, is one of those things that you basically see it everywhere. You know, these days, every company that wants to basically build pipelines is just focusing on building a DAG. Why? Because actually makes it much easier from the task manager. Okay. So now the idea of DAG is that it's a directed graph that doesn't have any cycle. Basically, ML pipelines are normally or usually are DAG. You don't see in practice to have any cycle in DAG. But it's possible if someone built the pipeline to have a cycle, but it's not a practice or practical step. Basically, what is a DAG? Basically, DAG is you can think about it as kind of like a blueprint of doing certain sequence, basically, or certain task in sequence by keeping into account the order of the tasks. You know, that's just kind of like the idea of DAG. Let's say, for example, let's say you are, for your data pipeline, you are working on, you're trying to basically build a DAG. And the first thing that we basically talked about is that be sure that, you know, the codes that you write are modular, you know, to just have a proper practice. So instead of, also same for your DAG, instead of having one function that does lots of job on your data preprocessing, write a smaller basically function to do that. Maybe what you have we have a function that just downloads the data. Then you have a function basically that just, I don't know, like just do certain cleaning, like certain cleaning. You just, let's say we're doing one simple cleaning here. Then you have a basically function that I don't know, like checks for data schema. You know, maybe you have a function that does, I don't know, some statistical analysis. Then you have a function that, I don't know, like does data split. Now the order doesn't necessarily mean like I'm just writing. Now let's say you have these 5 functions, and after the data split, you also have one function basically store the data. Okay. Now you want to build a pipeline that, you know, is just using DAG that basically creates this. Now we will have lab on this later, but let's say, for example, think about your DAGs. Imagine you have a canvas, an empty canvas, and you're going to basically start drawing in it. And every one of these function is going to be basically one node in that basically drawing that you do. So maybe you start with the download and you say that, okay, this is the download. So download, that becomes task 1. And after the download, I want to maybe do some cleaning. Basically, actually, let's do after the download, let's do data split. And after a split, we do like a cleaning. After cleaning, we do a schema. After the schema, we do statistics. They all start with S for some reason. And then we do a storing, right? So DAG basically says that I will create connections like this, right? Now, these connections, you know, could be all sequential. You also could have things that they can run in parallel. But the benefit of building a DAG is that you basically create these dependencies for your basically pipeline. Now, if you have something like that, then there are some platforms that they help you with the orchestrations, you know. So you're basically using a certain, basically platform that helps you with the orchestration of this task. All you need to do is that to ensure that you have the platform basically installed, you have a DAG, and basically you let that basically that platform to access the stacks, and it automate the process for you. And now what we will see is that one of the things that we will work in this class is Airflow. It's one of the common industrial, it's just platforms that we use for orchestrations. And Airflow, what it does, you can just think about this seriously as a secretary that just makes all the connection, makes all the call basically, or just makes all the connections. So Airflow by default doesn't have any compute or any like a GPU or stuff like that. It just makes the call and makes the connection, right? So we will have labs on those, but that basically becomes a definition of that. And for your data pipeline, which is going to be your second submission, you're going to work on building a DAG for your data. A DAG, multiple DAGs, depending on what you are basically building. Okay. And again, we will see more of DAG in details in labs, but that's the definition. Is that clear for everyone? All right, so now, pipeline orchestration frameworks, basically, as I said, so imagine you have all of these and you want to orchestrate this. So you need a pipeline orchestrations. They are responsible for scheduling various components in the DAG, basically, the DAG pipeline that you have. So you need some tool that orchestrates that for you. Okay. Again, these are example of Airflow, Argo, Celery, Luigi, Kubeflow. I think we have lab on Kubeflow, Airflow, and I think one of your TAs are working on a lab on Argo. Just the Argo and Kubeflow is like more like Kubernetes side of the work, and Airflow is just general, basically, just so. Now the next thing we're going to talk about is TensorFlow Extended, or TFX. So as I said that I personally work with TensorFlow, so we're going to just go with TensorFlow. It's one of those like a free libraries that you basically can basically work with. Built by TensorFlow team, it basically helps you it's like an end-to-end platform model, ML model production and deployment. It basically offers you everything from data ingestion to model serving. Okay, but let's have a breakdown for it here. So this is overall TFX components. It's like if you look at the TFX as a whole, start with data ingestion, validation, feature engineering, model training, model validating, or pushing if your model is good, and serving. Now, each one of those steps, basically what TFX has done is, before TensorFlow TFX or TensorFlow Extended, TensorFlow already had these components individually. You could access all of this, like TensorFlow data ingestion, data validation, transform, Keras models, TensorFlow model analysis. These are all libraries that you can actually pip install individually. So what TFX has done is that it basically packaged all of those together, create all the connections. So if you install TFX, you have access to every one of these, but they also kind of like interconnected, so you don't need to worry about those connections if you're not that savvy with TensorFlow. Normally the way that it works is that it starts with building some data, or loading some data, converting your data to basically TensorFlow format. And then it starts with the data validation. And again, that is going to be part of your data pipeline, not TensorFlow, but a data validation. And data validation is part that you're going to create a statistic gen and a schema gen. So you have this schema and you have this statistic. Okay. So why do we need something like that is you have a training data, and one of the things that you need to first do on your training data is that create a schema from that. And what is a schema? A schema basically means that it could be anything from, for every column, what data type is this column, what's the range of value for this column? So that could be your schema. Why that's important? Because when you build a model over your training data, you expect this column to be integer. Now, what if during the inference, that column is flowed, right? You know, that column has a different data type. So that's basically is not a valid schema. So you want to, you basically get during the training, you create a schema over your training, you carry that schema as part of your model inference. So every time new data comes, you match it with this schema that you have to ensure that this data matches the expectation that model has. All right, because in your model might expecting different data types, you know. So that's the schema that you have. And a statistic gen on the other end, basically what it does, we also need to be sure that the training data that, so let's say this training data that you are using has certain statistical characteristic for every column. Like for example, if you're dealing with the height, let's say height is a data point that you're using, and you have a mean, max, standard deviation, or I don't know, like a range, or like a different basic characteristics that it's you collected, right? Or if it's categorical, you basically know that how many categories was in this column. Like for example, you have 10 unique categories. As part of the inference, the data comes, and you're looking at this data, and we do some sort of basically called validator. So you look to see that is the new data that arrives, is it look like a normal data to me, or it's like an anomaly data? Because you compare it to the statistics that you have. If a data comes and looks like an anomaly, you know, you have a decision. Either you want to basically move forward with that data, pass it to your model, or just reject the data, depending on, or let's say, for example, you have 10 categories in, let's say you're looking at, let's say a certain disease, and you have 10 categories that during the training and during the validation or testing, you all of a sudden receive the 11th category, a category that you never saw during the training, right? Then the question here will be that what should we do? Should we stop this? Should we process it? Should we go back, update our schema and statistics because now we saw a new category? You know, those are things that we will talk about later. But that's why you need this. So basically, every data pipeline need to have some schema from the training and some statistic that you compare to. Okay, so and then this transform part is that comes around whatever data feature processing engineering that you do. You basically ensure that that same transformation that you use during the training will be used during the inference. Okay, one of the worst thing that you want to do is to do conversion. Right? I personally have dealt with that. It's I don't have a really good basically like a memory of that. The problem is that we were building, me and my team, we were building in Python and all the components that we have, but we decided that our product is only going to do C++, right? And okay, so then that means we need to pick whatever we already built, because we are not going to rebuild that one. Try to convert it to a C++ code, and you never get identical. You cannot do one-on-one basically mapping. And we ended up with like every time we test, and we're like, well, it kind of look like it's working. But then when you run it, actually, you see that lots of discrepancies in the conversion. And they pile up and it becomes like a compounding effect. And you see lots of error happens. You pick the same data, you run it through the pipeline, Python pipeline, it works. You run it through the other pipeline, it doesn't work. So that's really important. This transform part, it's really important to ensure that you don't end up doing what I did, that means to do in one language, end up converting it to a different language. Now, there are things that we will see later is that there are ways that you can improve this scenario. One of them, for example, if you deal with neural network, is that by default, maybe when maybe you do neural network, you have this data processing, and then you have your neural network, right? That's normally something like that. But these days, you know, especially PyTorch, TensorFlow, they have these capabilities that maybe I don't need to have this outside of the model. So you basically, when you build your neural network, the early layers in your neural network are the pre-processing layers. You get the raw data, pre-process the raw data. And then the later layers becomes your actual model layers. Okay, so the first maybe 4 layers does all the pre-processing part of the model. Then if you do something like this, that means this becomes your model, basically, together. The benefit of this is that this neural network, at the end, this larger neural network, when I am done with the development, I basically do a frozen graph, I basically export it, right? And I use the result, the exported model, on either on the edge or basically in the cloud. But every time I want to do inference with this model, I don't need to worry about this. I don't need to do any code conversion. Because this model has a frozen graph of pre-processing. So you don't need to worry about anything. This becomes language agnostic, right? Because it's a frozen graph and you can load this frozen graph in Java, in Python, in C++, just, and without any basically discrepancies. So now this you can do that with the libraries, and this is really recommended. However, it has caveats, right? Anyone can guess what do you think could be the caveat of this? If we do something like that, add the pre-processing to the model.
Size increases a lot.
The size increases, what else?
We can tightly couple, so any change that needs to be done, irrespective for any one of them will cause a change to the other.
But that's also a good point.
If the data is out of distribution, then it won't be able to process it.
Process it, some covariate shift, you mean something like internal shift? What else?
We have to train the model again if we try to.
Yeah, your friend also said that, something like, so these are all correct, actually, these are all good points. So one of your friends says that if you want to change something about the data now, you need to change everything about your basically model. You might be able to do some workaround around it, but not necessary. That's a good point. Your friend also here said that if something changed about the statistic of the data, then you might not. But that could end up having some sort of like an internal shift in the data or the data that you receive, which leads to a bad result. Those are all correct, but those type of things, if it happens also without having that part of your model, like let's say you have these two separate, those type of things even could happen at that time, right? So that's a same, basically you're in the same, dealing with the same problem either way. But here, the main challenge that you end up might having is that it's going to be more time consuming. When you do inference, because the model now need to do data processing and the inference for you. So it becomes slower from the perspective of every time you make a call to the model, it becomes slower. Versus if this was outside of the model, you could have a different system that takes care of this, maybe pre-compute those, have them ready so quickly model can basically access the pre-process the data, pre-process data. So that could be challenges. But again, it's really important this transform whatever you do during the training, exact same things you apply during the inference, basically. And then you have tuner and trainer, which is like for hyperparameter tuning and just training. You can do some evaluation of the final model to see that how good is that model. And you can do infra validator, which infra validator is kind of like here you validate the model against data. Here you validate the model maybe against system. Like if I want to run this model now on this system that we have, will it work and stuff like that. And then if it works, then you push it. And then you can serve the model basically to make inferences. All right, so this is just an example of Hello World with TFX. All of that, the steps basically goes through. And then at the end, it allows you as part of the pusher, you can serve the model as a TensorFlow hub. You can serve it as a JS model, TensorFlow Lite. And you can also use TensorFlow serving. So there are 4 different ways that you can serve that model, basically. So now, just a summary of what we went over all at this point. So now the next one, we're going to talk about the collecting of the data. So and the importance of the data, we're going to go over that. So when I was doing my PhD here, there was this advisor that I used to work with, and we were doing this project in hospital, and We needed to collect our own data. And the project we were doing was actually for a queuing system. And we were doing something like operation research, was like an optimization of the queuing for the hospital's beds and rooms. And what me and the other fellow students basically we basically used to go to hospital, wait in the hallway with basically Excel sheet and just time everyone that when someone is using the room, because we didn't have data. We needed to basically do that manually. And first thing was that it took us a while to get that approval. You know, it's not that easily that let you to go in a hospital and time something, right? We could just go through process, get the approval. We need to go some, it's like get certain certificates to do that. And so that's one of some of the challenges. You know, data is important, but also it's not easy to acquire. Like sometimes it's actually really challenging to get the data that you need. Now, we need to basically, we're going to talk about the data quality. We're going to talk about the data pipelines from collections, ingestion, and preparation. And we're going to talk about the after, basically, you know, there's after serving the model for the data collection and monitoring, basically. So we're going to talk about three things. So same thing here. Now, first thing, it's actually really interesting code here. In ML, data is first-class citizen. Well, that's an interesting thing to basically memorize or remember. When we deal with software, in software code is the first-class citizen, right? That's in software engineering. In ML, it's the other way around. It's like a data is the first-class citizen. It's like that tells you how important is the data. Now, also, there's this terminology to, you know, just remember software 1.0, software 2.0. I think if I'm not wrong, this was introduced by one interview to software 2.0 by Karpati, Andrew Karpati in one of the meetings or the interviews. I think that software 2.0 terminology comes from there. But in software 1.0 or the traditional software, basically you have some explicit basically instruction for the computer to run software, right? That's a software 1.0. And software 2.0, technically, you can just think about it like we don't give that infrastructure, or we don't give that instruction to the computer to run software. We give the data, the model, and says that you find out that instruction. Right? The model, that's basically how we train machine learning models. You have the data, you let the model learn those patterns, basically how to map from X to Y, you know? So that becomes the software 2.0. But also, you know, just remember that good data is always the key for success, and code in software equal data in machine learning. Now, it's also really interesting. Anyway, so it basically says that this is your machine learning system. This person answers, yep, pour the data into this big pile of linear algebra, then collect the answers on the other side, and says, what if the answers are wrong? Just stir the pile until start looking right? That's the whole idea. Like you have this data and just, you know, it's just we change the model, change the parameters, just stir it. Now, important to remember, your models are not magic, you know, just models at the end. You need to have meaningful data. That means maximum predictive contents. You need to be sure that you have removed the non-informative data. And again, as we discussed, you need to be sure that you have feature space covered, you know. So it means your data that you are using should have really good set of features. You got rid of the noisy features. Also, overall, your data covers the population that you are targeting, basically. Now, also remember this. Garbage in, garbage out, right? So it doesn't matter how good is your function. If your data is garbage, you get a golden garbage back. You know, just that's reality of that. So now when it comes to data pipeline, again, you basically need to think about data collection, ingestion, data formatting, feature engineering, feature extraction, all of those, you know, just again, these are just example of that data pipeline. But it doesn't just, your data pipeline, it doesn't just end at the data stage. It's actually after you develop the model and after you deployed the model, because it's really important for you to keep monitoring. And when you monitor, you get new data, right? So you get data around your downtimes, error, distributions, if there has been some shift in your distribution, Is there any data failure? Is there any service failure? These are all data. These are all new data that comes to your system, right? And you need to also monitor for that. So that means when you build, when you have you building a data pipeline here, but you also probably need to build a data pipeline here, to be able to basically use this information. And normally, if depending on how is the system, but if you're doing like if you're collecting this information via log, maybe you don't need the same sort of data pipeline. You just need to stash these logs in a proper, basically service and convert that log to maybe some tabular data or some like a visualization that gives you that information. We'll have those later. Now, there are a couple of key points we're going to talk about. First is that whatever you're building, be sure that you understand the user and you can translate user need into your data need. Okay. The next thing is that to ensure that the data coverage is high, you have a good data coverage and high predictive signal. And you need to be sure also you can source and store and monitor data quality response. Okay. So that's really important. I'm going to go one example and we're going to break those down. So we already have talked about this, like the application, running application that we have been using in the class. What was the idea? So who's the users, some runners. What was the user need? User wants to run more often. That's why you're building this app. Your goal was that I'm going to build an app that offers more run to users because users are kind of like tired of themselves, to find the run path and they want to run more. So the user need is that they want to run more. User action is that, they complete the run using the app. You offer them basically a running app or running pass and they accept it and they complete the run. And what are the output of your ML model is that what routes basically user need to run on and when to suggest it to them, like based on maybe a time or weather or something like that. And what's your model learning? It's going to be patterns of behavior around accepting the run. Like for example, let's say your app suggests user, it's a good time, maybe in a half an hour, the weather is good, go on a run, right? And user doesn't accept it, like user reject it. And you do that maybe another day and user reject it. Maybe you need to learn that, okay, maybe this time of the day that I'm offering to user, maybe they cannot go on the run this time of the day. So just your model be able to learn that feedback, from whatever user is giving, completing the run or not completing the run. If you offer a user a run, they start the run and they complete it, maybe that's a good sign. But if they start the run and they never complete it, that maybe that's a bad sign. Maybe as a feedback that maybe that the run that you suggested either was boring for the user or was too like a difficult, challenging for the user, or something. So basically your model should be able to get this feedback. Some of the feedbacks you directly get from user, some of those you can infer based on basically based on the result that you're seeing. And then you also overall you want to be sure that you improve the consistency. So like if the user is consistently using your app, that means they're happy. But if the users start using your app and then slowly over the time they're degrading or they start not using the app, that also could be a sign that there's something is wrong. So now there are some key consideration. First one is come around data availability and collection. First consideration is data availability and collection. So question, what kind of data do I have? How much of this data do I have? That's always like to be a question. How often this data comes in? Is it like a annotated data? It's like, do I have label for this data? How hard or expensive is for me to label this data? Those all becomes some questions that to answer. Then you also need to be sure that we can translate user need into data need. What user need basically means that if you know that user wants to run more, what do I need as a data, as a features to help user basically acquire that or achieve that basically goal? That's how they can basically, your idea is that how can I use my data or what type of data, what type of feature I need in order to be able to do that mapping, okay? Now, let's say, this example of the data set for the same thing running app. So you have 3 running here, Boston Marathon, this is Seattle, October 1st, 5K, Houston Half Marathon. You have some runner times, you have some elevation, and you have basically, it wasn't fun, basically, or not, all right? Now, so you basically have series of features and you got some basically label as an output that if the user liked it or not, you know. Now, the question here will be that, think about this, like if you, what would have happened if you didn't have, I don't know, like the elevation, okay, as a feature, right? If you didn't have elevation as a feature, maybe, because, you know, like you didn't account for elevation, basically a run that basically here 3 hours and fun was low, but if the elevation didn't have elevation, maybe you would assume that user enjoyed the running for the Boston Marathon, you know, because it's just it's fun, you know. So it's important to think about the features that you have used as part of your model that helps you to map to the user needs also. Now, also be sure that you get to know your data, identify your data source, where this data comes from. You know, it's just really important, especially these days. We are in an era that, you know, the internet has lots of bad data, you know, just like called data poisoning. So it's really important that whatever data you download, open source data, be sure that the source of that data is actually like trustworthy. It's not just random data that you find online. Again, there are lots of challenges with those type of like unknown data. One way is that, for example, check how often that data was refreshed. So when you're looking at some websites to find data, see when was the last time this data was refreshed. It's like a really old data because normally they have timelines. So do you see the tags on when was the last time they have added to this data? Check for consistency for values, unique data types, monitor for error, outliers, this type of things basically. Then the next thing is that data set issues, you know, you need to be sure that you figure out the data set issues that you have early enough. A simple example is that inconsistent formatting, maybe 0 versus that 0, you know, that could be, you know, and translate differently, you know, from the model perspective. Account for compounding error from ML models. Basically, you know, if you have a series of models that they feed to each other, you account for those. Be sure that you monitor your data source and system source for any sort of issues and outage. What happens if all of a sudden, like there's an outage, there's like a network, that network is down or something, and user is using my system. What happens to that data that I'm collecting? Can I get that data later back, you know, when the network is back? How fast can I get that data back? So think about a scenario like you are serving a software to an organization and they have your software installed on all their machines and they have thousands of machines, right? For a day, this the internet or network is down, but your algorithm or your model basically was working in the background and you keep collecting data. Now, when the network comes back, you need to think ahead of time that should I just send all the data right away? What do you think? Well, why not?
Take a lot of your bandwidth.
That's correct. If all of a sudden, as soon as the internet is back, you start sending up the data, you're going to basically take all the bandwidth from the network, right? And you could cause additional problems, or you could basically, I don't know, like there's certain IT rules out there like that. If you take above certain basically bandwidth, they can easily ban your software. You know, it's just kind of like, so you need to account for this ahead of time. What happens if something like this happens? Maybe instead of sending everything at the same time, I already have indexed the data. I gradually send the data, right? You know, I start sending the data from right now. Any past data that I haven't sent, I slowly basically send those up, so I don't basically impact the network. So now the next thing is that to measure the data effectiveness, if you know, just be sure that you have this idea in mind that intuition behind data could be misleading. Some features basically might have put in your might have, you thought that they have predictive signal, but they end up not having, just keep those in mind. Be sure that you do feature engineering and you do feature selection. Feature engineering will help to maximize the predictive signal because you built new feature to improve that predictive signal, and feature selection helps to measure the predictive signal. Because when you do feature selection, you look at all these features, see that which one of those are useful, that helps the model accuracy, which one of those are not, so you remove those ones, the ones that are not basically useful. And again, translating user need into data. Data need is, you need running data from the app, you need maybe demographic data, you need local geographic data. And again, this type of data, definitely you cannot just collect those randomly from user. You need to be sure that you have basically consulted maybe a lawyer or something. If you're collecting certain types of data, like a GPS data, you need to be sure that you basically have right to do that. You basically also have told the user has agreed that you can collect this data. From the perspective of features that you need, because again, maybe this is running up, maybe demographic, time of day, run completion, pace, distance, elevation gate, heart rate, those type of things that you can collect. And again, you have the permission to collect. From the labels perspective, try to, as much as possible, to see if you can get the feedback from user. If not, if they don't directly give you feedback, try to see that if you can infer the feedback into a label, like again, example is that user starts a run, they never click that terminated, they just close the app. Sometimes I have done that while running. I'm at the end, I just close that red and go to the app and close it. But if you have the GPS and they reach to the goal, you can assume that they did the running, just you can make the assumption that they did finish the run. You can basically do some inferences like that, but with precaution also, not directly. That finishing the run doesn't mean that they enjoyed the run. If you're trying to say if it was enjoyable or not, maybe that's not the case. All right. So these are the key points that we just talked about to understand your user, translate the need into a data problem. We talked about how much, what kind of data, how much you have, what are the details and issues of your data, what are the predicted features, what are the labels and that you're tracking, and what are your metrics. Just also remember that you need to have those ahead of time. Know that what's the metric that you're basically measuring. Now, the next thing is pretty important. It's comes around responsible data, security, privacy, and fairness. We're going to talk about data sourcing, data security, and user privacy, and we're going to talk about bias and fairness in the data. Okay, so let's take a short break, and then actually we continue from there. Took much longer than expected, but so we're going to go back here with. So we're going to talk data sourcing, security, privacy, and bias and fairness. This is an example that the classifier was trained on open source data. So the idea of this classifier was that this is a paper for it. I think we have it actually on the canvas. But the idea was that to make image classification for wedding basically photos. So the idea was that to detect if this is a wedding photos or not. And as we see, ceremony, bride, ceremony, and just person, people, right? So what does this tell you? This tells you that, this classification, or basically because of the data, the publicly available data, only has learned that maybe westernized weddings, to be just the case that it can predict. For certain countries, certain demographics, it's not able to make the prediction. Right, so that's an example of when you have some sort of like a bias in your data, because your model, you're serving that model to everybody, but not everybody can use that model, right? So that becomes an example of that. So another thing is that when you source your data, be sure that you can source this responsibly. If your data comes from different places, you can build synthetic data. I think one of the groups wants to do that. You can find open source data set. You can do web scraping, basically. You can build your own data set that is not synthetic, like building a data set. Or basically you could collect live data. There are different ways that data could come, and each of those has its own challenges because normally you don't have label for lots of these data. Now, then the next thing is that data security and privacy. Just be sure that, when it comes around about data security, it's like whenever you collect users' data, how can I secure this data? Well, how I can guarantee the user that the data is secure. Okay, you always need to think about what will happen if I have a breach. Okay, I collect data as user. What will be the impact of that? You need to think about something like that. And privacy comes around you need to ensure that you keep your data, users' data basically private. It's just like you don't reveal those unintentionally or in some circumstances. Be sure that you give user control of the data, what you're collecting. Don't be one of those apps or softwares that they give you a long list that no one reads it and they collect everything. Actually, I'm going to publicly talk about it. It's this rings that I've got for tracking, activity tracking, Aura. And after I got the ring and I read it, I was like, wow, this is such a piece of crap. It's collecting everything, and it tells you that we sell everything to everybody. It's literally reading, right? So, and I'm stuck with it now. It's just, but what I have done is and they charge you $6 a month to use the app. All right, so I first canceled the registration, and then I disconnected my phone, app from the internet, so you cannot basically send my data out and just have a ring on my finger. So don't be one of those apps that they collect everything and we sell everything if you want it or not. So now, then also remember that the compliance. You just remember that you need to know the regulation and policies of where you are building, the country that you are, the state that you are. They all have different regulations, so you need to be sure that you understand that when it comes to data collection. When it comes to user privacy, you need to protect the personal identifiable or the PIIs. Be sure that if it's not necessary for you to have individual level data, then do aggregation, because that way you guarantee user privacy. You need to do some redaction. That means that you remove some part of the data so data doesn't look like you cannot map the data back to somebody. The data redaction is pretty difficult. One of the tasks that we do at our company is we try to find those elements in the text document, and it's really challenging. The best companies out there, Google, Amazon, Facebook, that they do it online, they have about a 90-something% accuracy in detecting the PIIs. It's pretty challenging, and I think human level performance for finding person a private data, I think it's 92% for healthcare data. It's a really challenging task. Lots of startups working around this type of ideas, to read documents, extract sensitive information, and maybe redact those, replace those. So that's for the user privacy. And the other thing is just overall know that how ML system can fail users. So this is just 4 examples of what could happen. Representational harm. It's the idea when your ML model amplifies stereotypes, negative stereotypes about somebody. Okay, because that's called representational harm. And I think that's one of the things that ChatGPT at first had issues, before this guardrails, all the guardrails to come around it. And models easily can basically memorize that. If the data is bad, models basically learn those information. Opportunity denial is the same thing that I always talked at the beginning of this class. Imagine you apply for university admission and you just get rejected. From the model perspective, it's just one false positive, but from you perspective, my perspective is that basically impacted someone's life, right? So that's opportunity denial. Disproportionate product failure is when the scenario that your product doesn't behave the same for everybody. Certain groups, they get higher basically acceptance, certain group gets a lower acceptance or like something like that, you know? Or if you're doing a recommendation, your app by default recommends certain companies more than the smaller companies because you had more data on those ones. That becomes disproportionate product failure and harm by disadvantage also. It's like when the scenario like that, your model automatically does some sort of like association between groups that if this group did that, the other group was going to do something like that. So it's kind of like a harm by disadvantage. Okay, so these are pretty common in ML models. You won't like it's pretty hard to find data and real life data that does not have bias. Right? In reality, data, they all have bias. Bias could come from so many places. If even from the the data collection step, bias could come because think about data collection. You could easily, like I say, I'm collecting data, and I could like when I told you like I went to hospital to collect data, I could introduce data collection bias. Why? Because I could only go collect the data from certain hallways, certain times. You know. That becomes selection basically bias. Like I don't select the other hallways. I don't see the full picture. Or you are basically trying to collect data for demography and you only collect certain basically zip codes. And those zip codes maybe by default are basically more like a higher end basically neighborhoods, right? So it's like you have this bias towards it. So we have a paper actually, it's on the Canvas bias, and there are two papers, bias and fairness. Highly recommend you skim through the bias. It gives you an idea, like there could be all sorts of bias that you could basically deal with. You know, from model perspective, from data model perspective, algorithmic perspective, it could be even engineer perspective, like an engineer that is building the app could have mental, like a mental bias, like about like certain tasks. Like you're building it, you already have this predetermined bias, and you basically like indirectly basically you introduce that bias to your model. It's highly important. It's at least in Europe it's more popular. In the US it's like for some reason not, but highly recommend them. Then be sure that you commit to fairness. Your model should be fair for group fairness. You need to monitor for group fairness, equal accuracy, or accuracy parity, or you monitor for you can even monitor for individual fairness. So group fairness means that if I bring the data and I look at my data from the perspective of two groups. Let's say I have like a gender, for example, let's assume we have only two genders in the data, like male, female, and you're looking at this perspective and say that what's the like a percentage of like a positive rate for this versus the other group, right? So if one of them is higher than the other one, and that just means that that's not a group fairness. Like if one group automatically, your model always gives a higher prediction for, that's not a group fairness. You can also go to individual fairness, like the different ways that you can slice the data. We're going to just talk about it quickly. Just be sure also, you always remember that, bias in human labeling and data collected, it's just also, that always exists. Data comes from some human, or someone collect that data, someone has labeled it, right? So you will find some bias over there. And also ML model can amplify the biases. If the bias is in the data, ML model will learn it and they will amplify that. Okay. I'm going to just iterate on that in a bit, but this is another example of bias in data representation. This is the population that you can get the data from. This is the data that you have. So you use this part, you build this model, and you try to serve this model to everyone, right? So that becomes bias in data representation because and an example of this could be you're building a model in US and most of the data that we basically have is just data from US, and then we serve that model in other countries, right? So definitely they don't get the same result that someone that in US using that model, just unless that the company has that when they're developing it, they have accounted for where they are targeting basically, okay? So And then for reducing bias and designing like a fair labeling system, just be sure that you account for different ways that you can basically improve the labeling if you're not using human labelers, basically. But overall, you can do the labeling by humans or some automation. And we will have some lab on weak supervision, and we already have talked about raters, and we can actually talk a lot more about raters overall. But just be sure that if you have a proper instruction for the labeling that you could provide before labeling, maybe that could help to reduce that or improve the labeling fairness. There are types of labelers or raters that basically you can use part of labeling. Generalist, it's like more some sort of crowdsourcing tools. Like generalist is like let's say I want to just do an labeling over the like a English like a text and or like a transcribing. And generalist means that anyone who's speaking English fluently, they can be doing the task. Subject matter expert is like become someone who's expertise in the task. They're more expensive normally. And your user is technically the best label that you could get is user if they give you the label, which most of the time is not happening. But if they can provide you that, that's great. So, and the key point here is that ensure rater pool diversity, investigate the rater context and incentive, evaluate raters tools, manage your costs and determine some freshness and requirement. So it could be some points that you can keep in mind to improve your data, basically labeling process, just overall. Now, before I move from here, what I want to quickly talk about is I did say something about data slicing. Now, one of the things that normally we do, in academies is that when it's just let's say you have a model and this just say that's that you look at the and like RSU curve and you get something like that, okay? And you look at the AUC area under the curve and you're like, okay, it's like a 96%. I have 96% basically, let's say 0.96. That's great, okay? And the challenges with this type of metrics are that these are like an average values, right? So that 96 doesn't mean that you actually perform 96 for everybody, okay? So there's a technique called data slicing, and the idea of data slicing is that you, from domain knowledge, for example, you look at, or just by looking at your data, you find some categorical features, like maybe ethnicity, gender, maybe zip codes, age groups, and stuff like that. And you bucketize your data, and you figure out the performance of each bucket individually, okay? So this 0.96 is for across all the data that you have. Now, you run the same thing across different buckets. Maybe you find that there is a group that is almost one, but then you have this group that is like this, then you have this group that's like this, and you also have a group that looks like that. On average, you have 96 because you have more data on these groups versus this one. But this one does even less than 0.5, like less than random. Right? So techniques like data slicing allows you basically to slice your data into buckets that either from domain expert, like what to monitor for, or you look at your categorical features or something that your data has and you bucketize, and you run basically your model against those. Your model will be fair, okay, basically without bias or bias-free, if your model basically performs the same across all of those basic groups or data slices. If your model doesn't perform across the same, then it means that you have bias towards certain basically slice or certain category. Okay, so that's one of the tests that you always need to do. And for some reason, it's not that, it's been kind of forgotten in industry. Why we know that? Because Every other day, there's a company gets sued and because the model does, especially when it comes to like anything like insurance claims or stuff like that, it's like getting sued because the model is tends towards certain demographic and favors towards the other ones. And the banking has these problems, issues. It's like you reject so many loan applications for a certain group demographic, and the other demographic gets a higher acceptance rate that they have. And that comes from the nature of the data and the model basically it has. Any question on that? All right, so let's do one thing. So I'm going to stop this for a second. Okay, so in the GitHub repo, this is on in the GitHub in GitHub Labs. It's going to be lab 4. Okay, so there are two main folders here. One is the SRC, the other one is test folder. And in the SRC, there's a file train and save model. Okay. Now the idea here in train and save model is that basically we assume that we have this GCP project. We have already basically created a bucket in the GCP. Like that's the same thing that we did in the previous lab. So I have this here. So I already have a GitHub. So I have a GCP project. In the GCP project, I have built a bucket. Okay. Additionally, I also have created, activated the artifact registry. Click on it. So this is artifact registry. And just you can think about the artifact registry as a place that you can basically send those artifacts. You register the artifacts. And here basically all the, let me zoom in. For this project, I have this GitHub GCP lab, and every time I get a Docker image, and whenever I basically create a Docker image, I basically upload it here, model the image, okay? So that's the idea. So we have a bucket for data and model itself that we store in the bucket. And we also have artifact registry, which the idea will be that to send the Docker image. So the goal that we have for the lab is that as part of our CI/CD, every time the new code goes to the GitHub, we're running a series of tests, and those tests is going to be done via a mock test. If everything was green light, that means the mock test was good. Now we basically want to integrate like that, whatever package that we have, package what we have the code, and we want to deploy it. And here in this scenario, it comes to deliver it, push it to the artifact registry. Okay, so that's the goal that we have. Now, the basically in the lab, first I'm loading this load.environment, basically just for loading the environmental variables. And as environmental variable, the only thing I have is this, the name of the bucket and the file version for this file name for model version. Okay, so the name of the bucket is the bucket that data and model will be saved to. And that file model version.txt is every time this CI/CD pipeline runs, one of the things that I want to do is that to check with the bucket and says that, hey, what was the previous model version? And let's say it tells me the previous model version was model version 3. And I said, perfect. Now I know it's 3. I increment it to 4. I send a new model to the bucket. Then I go to that file and change 3 to 4 because now the model version is 4. So that's the idea. No, it's not the best way of doing it, but just practical for the example here. Okay. So now I'll go back to this file. So I first load the bucket name and the model version name from environmental variable. A bunch of basically library that we import. One of them which is important here is this from Google Cloud import storage. So in order to make a connection to the bucket, you need to work with that storage, and the storage is for the bucket basically. Okay. So there is this function to download the data, which is just a function that calls to scikit-learn and gets the iris data. Is it iris data? Yeah, iris data. Okay. The reason we made the function is that we want to also be able to test it as part of the mock test. Okay. Then we have this function for pre-processing, which just pre-processes some data. We have this function for train model, which trains a random first model and returns the model. And then comes from here, get model version. Now, in order to get the model version, we need to. So remember, we have this basically GCP. So this is our GCP. Part of our GCP, we have a bucket, right? In the bucket, we have model version and model file, and we will also write the data over there, basically. So we need to make a connection. Let's say from my machine, we want to make a connection to this bucket, get information. It's like a two-way connection. I can write and I can read, right? So in order to do that, we're going to use that library that basically we imported, the storage, from the GCP, GCP, we imported storage. So the first thing you need to do in order to make a connection is to create a connection, basically. And in order to make this connection, we call this a client. So we are a client to make this connection. So start from here, basically storage.client, right? You initiate yourself, your computer, as a client, basically. Okay? I want to make a connection. Then the second line is really, I'll give some space between the lines. It's easier to. All right. So the second line is basically, we have a connection. Now we need to say which bucket are we accessing to? Because you could have a series of buckets, basically. So we basically say that this storage client, I'm accessing this bucket. You have the bucket name that we have. So basically, you made a connection and you say that I'm accessing to a specific bucket, like a bucket 1, for example. Okay. Maybe you have, again, multiple buckets. So you make a connection and then you say, I'm going to access this one bucket. Then, so you have access to the bucket. You want to see what is in the bucket, like access to the stuff that's in the bucket. So bucket.blob. So blob here is binary large object files, basically. That's the idea of blob. Okay. So basically, you say that I want to. You have the access to the bucket. I say that you tell to the bucket, I'm looking for a file name model version, right? As an object. You say that if exists, basically give it back to me. So that's basically how you get that. Bucket blob, I'm looking for this blob, okay? Now, you just have a blob, like a binary file. You don't have the file itself. You need to convert that file. If it exists, you need to convert it to the format that you want. So you basically say that if the blob exists, that dot exists, it already means that true, false. Then, so the file that we are opening, it's just simply has model version in it as a text, right? So blob.download as a text. It reads whatever is within the file as a text for you and writes it to this string. Okay. The next thing is that I also want to convert that string as a model version to integer because you remember I want to increment it later. So I just convert that as a string to integer. And if the blob didn't exist, then that means I haven't written anything to that file. I just set model version to 0. This is the first version that we are creating. And then we return the version. Does that make sense? So that's one call to just get the model version. The next call is that to update the model version, basically, you have a bucket name, version file name, and the version that you want to do. So same thing, remember, we want to make a call and just update, increment the number. So you do the same thing, you make a connection for the bucket name, and then this time, instead of get the string value, you upload from a string, right? You basically write the new version to that file. That's the only difference. The only difference is this line, basically. You write the new version to that file, and if it worked, you return true, else you basically return there was an error. So that now we have one function that gets the value, one function that calls and updates the value. The other thing is that we need to also check a way to see if the folder exists. What if we make a call to a certain folder, for example, for a model folder, but that folder doesn't exist, like there is no folder name like that. So this function basically it just checks to see a certain folder exists on your bucket, in your bucket. Okay, so we basically make a call to the blob for the folder name, and we say if it exists, or sorry, if it doesn't exist, then you want to create that folder name. And an easy way to create a folder name is that to just upload an empty string to that blob, it automatically creates a folder basically for it. It's just like a hacky way for doing that. Okay, so the other one is the save model. So let's assume that we on our model computer we have built a model, and now we want to save this model also here. Okay, model file basically. So same idea again. All the connection that we do is kind of replica. So basically, we make a connection to the client, the bucket name, and we check if the folder doesn't exist. We create the folder by sending an empty string, and then we basically upload blob.upload from file name. You know, it just uploads a file to the blob for you. Okay, so those are on all those functions. They have a really good documentation on Google. Basically, you can just find all the functionality that you can use blob with. So, and then this part, the main function, basically we put everything together. So we start by getting the version. At the beginning, we get what's the current version, what's the next version, download the data, process the data, develop a model. And after you develop the models, give a name to the model, save the model to the bucket, using all the functions that we defined. And at the end, basically, we check also if the like a current version was there, we just update the version with a new one, and then we do some printing. So that's it. So this is this code basically. It just does pretty a straightforward task. Is that clear for everyone? All right. So now. The next, so before I go to the test part, so we have a Docker file for it. In case you're not comfortable with Docker, we will have some Docker labs coming up, I think it's next week. But it's just, this is just this Docker file that we're using for this. So what I wanted is that we're going to later basically send this Docker, to artifact registry, okay? So just keep that here. Let's see, what else do we need? Nothing over there. So let's go to the test. So this is where our basically tests and mock tests are going to happen. So in order basically, there are a couple of imports, but the one that's going to be new for you is that from unit test.mock, import patch and basically magic mock. So that's what we are going to use for this mock concept from the unit test. And I'm going to see how it works now. So we're going to, because it's going to be a basically unit test, so we going to build different functions. Each function is going to test one of those functions in the train file that we have. So in the train file, we had 5 functions: download the data, process the data, build the model, check if the folder exists, update the model to the folder, and update the model version. Six functions. So we're going to build 6 tests basically. That means every time new code goes to GitHub, we want our basically continuous integration to run this mock test or this test. And if everything worked fine, then we continue with the process. So the first one, it's just a straightforward test. We have the download data and we check if the data exists. If the data exists or not. You're just doing an assert. Download the data, assert if you got any data. The next one is pre-processing. We pre-process the data and we just do a simple dimensionality basically check to see between test and train, everything matches. This third one, which was we want to test the function for training a model. we were supposed to build a random forest, for example, what we will do is that we build a model using the function train model, and we test if this model is an instance of random forest classifier. And we also be sure that your model has an attribute .predict. Because it's possible you build a model and then like for some reason your model doesn't have .predict and you deploying it and there's no .predict to inference, right? So we check to see if the model is random forest and also has an attribute called predict. Okay, so now here we are going to start building the mock test. There are lots of comments on this. We can read it later more in details. But the first one is the model version. We want to mock this test. If I make a call, I get the model version back. Okay, and there's another scenario that I don't get the model version back. But basically, in order to avoid your client, remember if we call to that function get model version, what it does, it creates a client connection, right? What we do here is that in order to not actually make the client connection, we are using this line with patch. We are patching this Google.client basically as a mock storage client. So what it does, that patch, it mimics basically that function. It doesn't actually make the connection anymore, but it mimics the behavior that we basically expect over there. Okay, so we are patching that client, this one. Then inside of that, now we are going to create multiple things. The first one is that we needed a bucket. We need a fake bucket. Okay. We also need a fake blob. Remember that binary large file? So we need to create those two. So we built it's called magic, basically magic mock for this both of those. Then we need to make this connection. So the first thing you want to do is that you have two fake basic objects. One is the bucket. The other one is the blob, right? There is an order for connection. You first put the bucket, connect the bucket to this mock storage client, right? Because you've marked that I have an access to the GCP bucket, the storage client, right? So I first say that I'm going to put a fake bucket in that mock storage. So how do you do that? Mock storage client, return value, bucket, return value, mock bucket. So basically this is the, so that means if our functions make a call to this, GCP client, and as a call, you should have get back like a bucket name. As a call, when you call, you're going to get this back, mock bucket. This is what we're mimicking basically. The second scenario is that, so now we have the mock bucket, we're going to connect the blob to the mock bucket. That means if I call to this mock bucket and it says, give me the blob, like the file that is in it, give me a basically fake file. So mock bucket, blob, return value, mock, blob. So that's basically the way that we make these connections, okay? So now the next thing is that we define basically we give it some input for the actual functions that we make call, because we're going to test our function, right? But in a mock way. So the bucket name, instead of using the actual bucket name, is some random name, bucket test. And the version file name is called version.txt. In the main functions that we have, if I go here, when you call to get model version, you need the actual bucket name and you need the version file version, right? What's the version file name? In the mock test, we just create some random names. It doesn't exist basically because we're making a mock connections. So now, step one, we're going to simulate the scenario where the version file exists. That means scenario that you made a call, there is a file for the version file. That means you already had some versions, like version 1, version 2 of your model. So you have that file. So how do we simulate that? Mock blob exists, return value true, right? That means like if I make this call and I say that is the blob exist, as answering, I get a true. This is just a fake scenario. What's the version? Now, we say that we're going to call to this function that we had, get model version, the bucket name, version file name. Okay? And because this is like a mock test, it actually doesn't make the call, and it runs under this, with patch client, so it actually returns us the mock value. So the version basically that you're going to get is going to be whatever the mock value we have here. Then we basically mock blob download as text return value 1. So this is the value that we are saying. So we are saying that we're going to return as a value the version 1. This is a scenario that we say there is a version 1 exists. Then we check. If the version is 1, then perfect. Okay. Now, we're going to do multiple tests here. So mock test. We say that we want to be sure that there was only, so this assert called once. This bucket name was only called one time, not multiple times. That's what the test does. Mock blob assert called once with this version file name only was called one time, right? And this text file basically only called once file, right? So it's just a simple. There are different types of tests you can do. I highly recommend you, when you go to unit test, look at the functions, all the basically details that you get. But it's just we want to be sure that we only called one time to every of these functions, not multiple times. So that's done. Now, the next thing we do, we reset everything. We reset like all the values that we set. Basically, we call to all the three, we say reset mock, reset mock, reset. So everything is resetted. Now we go to a second scenario, a scenario that we made a call, the file doesn't exist, right? And here basically we return false, the file didn't exist. The only difference is that if the file didn't exist, the model version should be 0. This is the first time. And then we assert the version to be 0, and we also need to be sure that it was called one time. So that means there are two tests. One, we assume we made a call, we got yes back, and we assume because we got a yes, there was a file. In the file, the version was 1. The second is that we made a call, we got false. That means there was no file version. Because there was no file version, the model version should be 0. Right? So both of this basically. And both of this we want to be called only one time. So that's one of the functions. I'm not going to go again through this one. So it's like it does similar thing, but we make the same basically client calls for update the model version. We basically mock assuming that we update what answers we are going to get. Okay, I highly recommend you just go through the code, and the test one is to ensure the folder exists. Same thing again, we just want to be sure that assuming that one time the folder exists, one time the folder didn't exist, what will happen? Okay, so, and the last one is that save model to GCS. We assume one time we were able to save the model to GCS, one time we were not able to save. So this becomes a mock test. So instead of actually making all this operation as part of your CI, you just assume that you tried every scenario. If any of this scenario happened, you should have been able to catch it, right? Without actually making the call. If something happened and you didn't catch it, then you will get some error. Or if something breaks down in the mock, you get an error but it's much faster, it's in memory instead of to actually making all this connection to GCPs, So it's much faster from that perspective. So let's close this. Now we're going to put all of that because so we have basically two files, a train file and a test file. And we're going to create a workflow for it. So this is the workflow that we are going to work on. This workflow works on push. If you push to the main branch, if you on a pull request, I put all of this so you see all the different versions. On a pull request from main branch, on cron schedule, basically, just timing, and workflow dispatch is you manually select run the workflow. So I put all 4 just as an example. Then here, environment. So I needed some environmental variable because as part of the CI/CD pipeline, after the tests are done, it trains a model and it also wants to write to the artifact registry. Okay, so artifact registry, let's go back here. This is the artifact registry. Whenever you, first time on your project, activate the artifact registry, what you need to do is that basically here, to do create a repository, you give it a name, let's say test, and you say, you see the format, Docker. That means every time I write something to this artifact registry, it's going to be a Docker image. Or it could be a Python file or NPM or whatever. And here there is a location. So I basically selected multi-region and US, okay? And everything else is fine, and I said create. So now if I want to make the call to this artifact registry to write something, I need to basically know that this, remember I told that if you have a different regions, you might have problems. So I need to, as an environmental variable, I know I need to write that I'm making a call to US section because I selected multi-region. So when you build an artifact registry and you see it here, for example, if you click on it and on top you see setup instruction, it tells you how you can make a call connection to this artifact registry. We're going to pick this code and just put it in the, basically our CI/CD. Okay, so let's go back here. So in environment, for a region, I put US, okay, because when you do multi-region, US stands for multi-region. If it's regional, it becomes East, for example, 1, East 2, and stuff like that. So it's like they have a different naming. US means multi-region. Then we're going to run series of jobs similar to other basically workflows that we see. We call this job to be build, test, and deploy. It runs on Ubuntu latest. And for me, in order to, maybe it could be a good practice for you also, in order to avoid this, whatever runs for, because I have all these labs together. So in order to be sure that I don't have these code issues, so I enforce the working directory to be only in this lab. That way, the workflow only sees that specific folder on my GitHub instead of every other folder. So I force that. Then what are the steps? Same thing as we saw previous class. Check out to the machine that you're connecting to. Set up Python, whatever version you want. Get the pip dependency basically. So if you already have cache pip information, use that, basically get that cache information if you have. If it's first time you don't have it, maybe. And then we install those dependencies. I'm upgrading the pip and install that requirement file, basically. So those are so far straightforward. And then we want to run that test file, that mock test that we have. So because it's a PyTest, for example, we say run PyTest, you pass it to the folder. It automatically finds out all the function and it tests all of those. And we're going to see that as we run it. Then we test if it was successful, echo that, for example. The next thing is that now we want to make a connection to GCP. So now this is not on my machine anymore, and this is in GitHub. So in order to make a call to bucket and also make a call to artifact registry, I need to make a connection to GCP, basically authenticate myself. And we did that in the previous lab also, right? So I already have key created from GCP account and stored in my secret variables on GitHub. And so basically what we do, we use this already existing action on GitHub to authenticate from the Google with GCP, and you just need to tell that what is the key you want to use for this authentication. Then we need to set up the Google Cloud software development kit, basically, it's for the command line here. So we set up that as also predefined, like by GitHub, you don't need to write. And then now we have access to GCP. We have the command line for GCP connections. Now we're going to write the command lines. The first one is that I will set the project to the project ID that I want, because otherwise maybe you have multiple projects, so GCP doesn't know which one you're connecting to. So you set gcloud config, set the project to name of this project, which is a variable, or here is a secret technically on my GitHub. Then we want to configure the Docker, which is the artifact registry. So authenticate yourself, and this is that line of the code that I picked from the artifact registry, the copy, right? The only difference here is that the region, basically, remember I selected US on top, that's the value. So you make a connection to artifact registry. Now you have the connection. Now we want to train a model and write the files basically. So the next thing is that basically we want to, this is the GCC bucket and version file name. We run this file that we had for train and save the model. It automatically saves the model. It also gets the model version for us. So now we have a model version. Then the next thing we want to do is that we want to build and push to the Docker or artifact registry. So what's the name of the image? So this is the name of the image, basically. Okay. Now, what do we want to run in order to Docker? Again, if you haven't worked with Docker, we have labs coming up with Docker, but first thing you build the Docker, you have basically a Docker image. The first thing you do, you're building it. After you build it, you push it. Push it where basically image name and environment is just automatically has the connection to the artifact registry. Then the next thing here is that because we're going to end up doing multiple calls every time. So every time we build a new Docker, right? So what we will do is that every time we change the Docker tag to a latest, or maybe instead of being latest as lazy, you could just call it production. That means this is your production version, for example. And the previous one now, the previous production goes to archive, for example. So you give a tag to your Docker image. Here, Docker, and this is the command line Docker tag, this one to latest. Again, you can, instead of latest, write production. And then you push that to artifact registry. So now artifact registry gets the Docker with the tag latest. That means this is the latest version. Okay. And then we say deployment was successful. Okay. So now we can basically test that. So if we go to actions, so this CI/CD pipeline, we can enable it manually, and we can just run the workflow. So it starts the job, goes through the process, and we'd see this also, I think, here. You can also see that there, but anyway. So this is done. So I'm going to go up to see this part. So here, run tests. That's the mock test that we had. So basically, it tells you that the test was done, and it tells you here on the bottom, 7 tests basically done, and there was like a passed, all 7. So it basically made all those mock tests, and you see it's pretty quick, because it's a mock test, right? If we want to do a real test, it would have taken a long time, for example. As building and pushing the Docker image, and after this is done, we should have a new Docker image in the artifact registry. Here, so if I go here now, and if I go to model image, just now, so this was this one, just now created, and the tag is latest. So this becomes your latest, basically, code or model or whatever basically you are creating as part of your CI/CD. So you do integration, test, and you do delivery or deployment, basically. Okay, so that becomes the whole idea. And now if you go back to your bucket also, you go back to bucket, you also should have, this model version was updated today, 8:57 p.m. and train model you basically have let's see, here, January 21st. Not a model version also. I mean, just as an example, okay? Any question on that? All right, so
So the tests are only done on the coding part, not on the GCP part. So the GCP will be totally, connection of GCP will be done by CI/CD, including GitHub Actions.
So so your friend is asking that we didn't test anything about the actual connection of GCP. The assumption is that you have all the secret keys and all the connections set. Right? We didn't do that as part of your. Yeah. You could basically have a test. Maybe first part of your test is that to make sure that you can communicate with GCP and your credential and everything is just verify those, you know. But assumption here is that you put those variables or connections secure in your secret and there shouldn't be any issues. But that's a good point, not necessary. That's the case always. So, all right, that's this one. So next thing we're going to, so we are done with the GitHub. And again, the rest as practice, you know, figure out. Highly recommend you just try those out. Now, the next thing we're going to do, we're going to work with MLflow, okay? Now, so what's an MLflow? So again, you can think of MLflow, a platform for experiment tracking, you know, for monitoring, training and deployment of ML model, and recently apparently GenAI models. They have it on their website as GenAI. I have been using it in the class and in practice to some extent, but not much. But I know it's pretty interesting the way that it works. So I highly recommend you to work with it for your project. The way that MLflow basically works is that, remember we talked about what to track. Like when you run an experiment, what are the things that you need to look for? So MLflow basically, as an experiment, it basically monitors for your model. So ML run means, model run means that when one time you run this Jupyter or this code, for example, that becomes a run. Every time you run, it basically creates some sort of like a run ID or experiment ID, for example. If you either assign it yourself or it becomes auto generation. Now, as part of the run, it basically keep tracks of your model, metadata, signature of the data, like a schemas, stuff that we talked about, examples, all the dependencies, all the pip dependencies that you need, all the conda dependencies. So think about every time you run it without even you doing it, it creates a file for your requirement.txt, environment.yaml, and everything. So if you want to pass this code to someone else to run, you don't need to worry about what did I use? It's already there. The file is there, so you can use it basically. Metrics, tags, parameters, and you can have multiple runs. And it gives you a really interesting dashboard that you can basically compare your result with your friend. So it's not just you. You can basically have a server that every team members basically writes, when you run the experiment, it's all written to a certain, like a bucket, and you can see the result of your friend's run. They can see the result of yours. They're like a team members. You can collaborate basically. You can compare your result with someone else's result. So now there are two scenarios when you work with MLflow. Either you do auto logging or you do manual logging. Okay, so auto logging, you just you're just at first you're like new to the MLflow and you're like, I don't know what to log for, or you're not sure even what to log for. You set that to auto logging. MLflow will take care of whatever it thinks is important to log for you. So that's the idea of auto logging. So it basically logs anything around data, model, metrics, result, and all of this. You could do manual logging, and that becomes your choice. So you manually decide, log this metric, log that file, log that data. You know, you need to specify. If you don't set auto log, then it only logs whatever you decide. Okay. So in order to work with MLflow, pip install MLflow, import MLflow basically. And this is just an example of like, I want to build a random forest classifier. So I'm basically running this. And here I said MLflow auto log. That means I let MLflow to log whatever is important. So in order to see the dashboard, you just need to run in the command line, MLflow UI, and what's the port that you want this UI to show up on. And if I run this, so comes here, and this is basically the, is empty. Let me do something. This came out empty, no log, so still empty. Okay, so I just did one run. And basically, this is the main page of MLflow that you see, and you see it says an experiment page. And this is the run name. It automatically generates a run name. If you don't specify, it automatically generates. And here, when you see here, it's a data set name, duration, model, and then if you you see there's a plus here. You can add this plus, and these are everything that it has monitored for you. So you can say that, okay, I want to get metrics. So it adds the metrics also for you here. And you can click on the run that you have, and you get this dashboard. It gives you some overview on who created, when it's run, where the addresses was basically stored at on your machine or at the network, and some information about the model's parameter, hyperparameters, and stuff like that. Then you go to model metrics. It gives you automatically some plot on the metrics of the model. You can change the plot. There are some plots that you can select, like a bar plot or density plot or stuff like that. If you have monitored for a system metric like a CPU, RAM, and stuff like that, basically it gives you that. This is the artifact. Basically, it tells you that the result of this run was one model. Okay. On the left, it says the model.pickle. That's the model.pickle. It tells you that this ML model file. It tells you that in order, for example, to run this model, these are what you need. Okay. And it tells you that this is the conda.yml file. If you want to install the environment as conda, if you want to do a Python environment, this is the Python environment file. And this is the name of libraries that you need. So everything in one go is packaged for you. You can basically share this with someone else that's running your code. It gives you this details about the random forest classifier. Also, it gives you this information how to make call to this model if you want to make a prediction. If you want to serve this model, basically it tells you that you can serve the model this way. So first you can validate the model, then you can make a call like this by prediction, making prediction. It also gives you information on, so for some reason I cannot scroll down, how to use the model on a pandas data frame, how to use the Spark data frame. So it gives you some tutorial also how to do that. So you can go back here. On top, you see there's something that says models. We don't have any models yet. We're going to see that add something, but let's see what else we have here. Anything else? So let's continue. So I'm going to close this. So the next thing is that basically I will run the same thing with the random forest. Wait, we did that, sorry. I need to go back. So now we're going to do this something differently. So here basically we're doing the manual logging, okay? So in order to do manual logging, whatever you want to log, basically you run it under MLflow start run. Basically, you basically, you will run within that context. That's the idea, okay? And here, basically, we build the model. And now I want to save the model. I want to register the model, basically. Now, in MLflow, in order to register the model, you need a couple of information. First thing is that you know, for logging the model, I need a model, a name, and something called a signature. Okay. Now, what is the signature? Signature is like a mapping schema from input to output, technically, right? So basically, MLflow says that like what data schema you need as an input for this model. And in order to understand what's the signature, there is a function that we import from MLflow models, import infer signature. And what you need to do is that make a prediction with the model. First, you have a model, pass the data to it, make a prediction. You call to the infer signature, you pass the X test, the input, and the prediction value. It automatically creates a signature for you, a schema basically. It creates a schema for you. So you just need an input and the prediction. Pass it to this function and it will create a schema for you, your signature, and you use that to log the model. You know, we're going to use that to register this model. So we run this. So it basically ran the model, says the model is here. So if I go on left, there's a folder called ML runs, you see? Inside the ML runs, there's a models is empty. Is 0. 0 is the name of the experiment. Every time I run, it's basically 0. If you don't change the name of the experiment, it starts with 0, increment 1, like that, experiment number. Within an experiment, you have different runs, okay? So this one was run 880, so it's this one. Inside it, there's an artifact folder. There's a model folder, that's the model, information, inputs, metrics, parameters, and so on. So they're all registered, they're stored on your machine. And when you run the dashboard, it basically reads from that folder and gives you those information. Okay. So if I run this, and we go back here. So now I have this latest one basically happened. So now let's say you have multiple models. You can basically select those and you say, I want to compare them. Okay. And you say that, okay, you want to compare what is the, like you have model metrics, also you have basically parameters, right? So let's say I'm interested to do, look at the training mean basically accuracy or error, and we are going to look at maximum depth, maximum lift node, minimum sample split, maximum features, or they all can end up being the same. They end up being like really identical. So, but hopefully we see something like a different lab. But the idea here will be that you see that these are all kind of like a flat here. The difference that they have is here. In this part is just the, I think this is the output basically, right?
Mean absolute error.
Yeah, that's the output, right? So basically one of them is 30, the other one is like a 29.8 something like that. But when you have series of models and you want to run those against each other, compare them, basically this gives you an easy way to do that. It has like a scatter plot, box plot, and contour plot basically. It doesn't have more than that. I don't know at this at the moment, but I know they're adding to this as they go. So, and the last thing is that if you want to load the model also, you can say mlflow.scikit-learn load model and the address on your hard drive where the model is stored. It can load the model and basically you can use that model for prediction. Okay. So we're going to stop here because I know everyone's getting tired, but I highly recommend you test this out yourself. Okay. Yeah. Stop this.